Welcome to this explainer. Today, we're unpacking a massive, totally urgent shift that's happening all around us right now. It's a fundamental change in how we build, how we operate, and honestly, how we judge the very spaces we live and work in. Our climate is changing so incredibly fast, and our built environment simply has to adapt if we want to survive. So we're going to dig into the hard data, the wild engineering breakthroughs, and some major reality checks that are forcing architects and city planners straight back to the drawing board. Okay, let's dive into this. 40%. According to the Whole Building Design Guide, our buildings are responsible for a whopping 40% of all energy consumption in the United States alone. Think about that. And 32% of that entire chunk is just from heating and cooling our spaces. Our buildings are literally starving for energy. And look, in a world that's desperately racing toward decarbonization, that massive slice of the pie simply has to shrink. But the impact of our built environment isn't just about the energy grid. It's about absolute financial survival in the face of climate change. The financial toll, it's already here. Just look at 2024 alone. Climate disasters caused global insurance losses exceeding $135 billion. That is 5 consecutive years where losses blew right past that $100 billion mark. Entire regions of the map are actually becoming uninsurable, all because the buildings there just cannot withstand this new normal of extreme weather. And the human cost is even more alarming. When these extreme weather events hit our dense, urban, concrete jungles, the infrastructure itself kind of becomes a weapon. It's a massive risk factor. The World Green Building Council projects that by 2050, up to 1.2 billion people, yes, with a B, are at threat of being displaced by extreme weather events like floods, storms, wildfires, and droughts. Which brings us to this terrifying realization: we are dealing with a shifting foundation. For decades, engineers would model building designs using weather data that was basically based on historical averages. They'd look back 15 to 30 years to predict what a typical year looked like. Well, that logic is entirely broken now. We can't rely on the past to build for the future anymore. We literally have to use extreme weather scenarios and forward-looking climate projections to design our world for conditions that haven't even happened yet. All right, let's look at our first big solution: retrofitting our existing buildings. To tackle this crisis, we have to start with the structures that are already standing around us. As this quote perfectly captures, retrofitting an existing building can oftentimes be more cost-effective than building a new facility. Before we pour millions of tons of new, incredibly carbon-heavy concrete, the absolute most logical first step is to fix the incredibly inefficient infrastructure we already have. Existing buildings make up the largest segment of our built environment, so conserving energy and materials right here gives us the absolute biggest immediate return on investment. Let's move to and see how this builds. When you're retrofitting, the order of operations is absolutely crucial. Step 1, you have to perform an energy audit to figure out exactly where the building is currently failing. Step 2, you seal the building envelope. Fix those leaky windows, the tiny gaps, the roof penetrations. And then step 3 is upgrading the HVAC systems. This is vital because putting in fancy new heating and cooling systems is completely useless if you haven't first fixed the leaky envelope that's supposed to hold all that air inside. So, moving right along to our next section, the Passive House Standard. So the crucial point is 90%. If we take those concepts of efficiency we just talked about to the absolute maximum, we get this incredible number. By strictly adhering to the Passive House Standard, you can reduce a building's heating energy demand by up to 90% compared to a typical structure. It requires so little energy that it can often function without traditional fossil fuel heating systems at all. It relies on small mechanical systems, solar gain, and, get this, even the body heat of the occupants inside. How wild is that? Now, how is a 90% drop even physically possible? Well, it basically comes down to 5 core principles. First up, airtight construction, which is measured rigorously with what they call blower door tests. Second is thermal bridge-free detailing, meaning there are absolutely no weak spots in the frame where heat can easily escape. Third, high-quality, ultra-thick insulation. Fourth, heat recovery ventilation. This is an incredible system that extracts stale air but transfers its heat to the fresh air coming in, actually retaining 80% of the heat. And finally, high-performance triple-pane windows. Put all those together and you transform a standard house into a highly efficient, entirely self-regulating machine. Okay, let's shift gears a bit. Section 3, Engineering for Climate Resilience. Efficiency is fantastic for mitigating our carbon footprint, but we also have to survive the storms that are, unfortunately, already locked in. A truly resilient building doesn't just sit there like a rock.
It actually acts like a living organism. According to the World Green Building Council, it must do 4 things: resist the impact of local hazards, mitigate the damage, adapt to changing conditions, and recover its function and value rapidly after an event. It's a totally active rather than passive relationship with nature.
And to meet these goals, engineering gets a little bit ironic. Enter frangible architecture. This is the intentional design of walls, roofs, or structures to deform, yield, or break in a controlled way during extreme events to maximize overall safety. Yep, we are now intentionally designing parts of our buildings to break on purpose. Think of it like the crumple zone on your car. By designing external facades or specific walls to basically blow out during high winds or massive floods, we relieve the pressure on the primary structure. This ultimately keeps the entire building from collapsing and saves the people inside. Which brings us to our final section, measuring real-world performance. We have all these amazing designs and theories, but the big question is, do they actually work? Well, to measure real-world performance, the industry relies on global benchmarking systems. And this brilliantly illustrates the big 3. LEED is famous for its environmental focus, cutting carbon and boosting energy efficiency. BREEAM excels at life cycle assessment and adaptability to the local context. And WELL focuses heavily on the social aspect, indoor environmental quality and occupant health. On paper, these systems cover all our bases beautifully. But here is the massive plot twist of the whole story: the performance gap. Researchers have identified this persistent difference between the projected performance of these buildings at the blueprint stage and the actual outcomes once people finally move in. Despite the super prestigious certifications and fancy plaques, many of these green buildings are completely failing to perform as expected out in the real world. You see, design expectations rely on perfectly idealized energy models, flawless weather simulations, and the assumption of basically perfect operation. But actual post-occupancy performance is a totally harsh reality check. What happens when a building is occupied by real, unpredictable human beings? People leave windows open with the heat on, sensors get blocked by furniture, and frankly, occupants usually have no idea how to operate complex, highly engineered thermostats. These everyday operational inefficiencies drag the building's performance way, way down. This leads to a truly fascinating certification showdown in the real world. For example, look at the Bullitt Center in Seattle. It achieved LEED Platinum and actually exceeded its energy targets. Why? Because it heavily utilized real-time data monitoring and adaptive controls. On the flip side, the David L. Lawrence Convention Center achieved LEED Gold, but post-occupancy evaluations revealed it actually failed to meet its energy expectations because of those operational inefficiencies. So a shiny plaque on the wall absolutely does not guarantee real-world success.
So, what is the actual solution here? It's post-occupancy evaluation, or POE, combined with real-time data monitoring. To genuinely fight climate change, these certification systems have got to evolve. They cannot just be static plaques awarded on ribbon-cutting day. They need to become dynamic, real-time feedback loops that are constantly measuring energy use, occupant satisfaction, and indoor air quality, allowing building managers to make critical adjustments on the fly. Which leaves us with one incredibly critical question to ponder. If our buildings are certified for the future, but failing in the present, are we truly ready for what's next? Next time you walk through your city or town, I highly encourage you to look up at the buildings around you with a totally new perspective. A beautiful blueprint is really just the beginning. True resilience and sustainability require constant adaptation, smart data, and a real willingness to confront reality. Thanks so much for joining me for this explainer, and definitely keep questioning the world around you.